Let's do some pretty basic 2D plotting, nothing really complicated, just enough to get you started. I think this video will end up being a little bit longer than I expected originally, but it still shouldn't be too difficult. Um, this is something that really threw me off when I first started using Octave and Freemat because it's really, really different from Maxima. Basically, Octave and Freemat don't plot functions, they plot points. Then they connect the dots. So if you want to plot a function, you're going to have to create points based off that function. But let's go ahead and start out by plotting a few points just so you can see what I mean. So let's say x equals 1, 2, 3, and y equals, let's say, 4, 7, 1. Now let's plot x against y. So hopefully you see what I mean, that this just took the points 1, 4. So the x value is 1, the y value is 4. Then the x value is 2, the y value is 7. And then the x value 3, the y value 1. So that's what I mean by it plots points instead of functions. It just draws the points and then connects the dots. The x in the plot command is a list of the x coordinates, and the y, so this is the list of the x coordinates, this is the list of the y coordinates. So let's plot a function by turning a function into a list of points. Let's go ahead and make this always on top. May not have much room here, but I'll be able to expand this back out in a minute. So let's we need to turn a function into a list of points. I first need to create a list of x values, a list of let's go ahead and just make a list of x values. So 0 to 10. So let's actually not hide that. X is going to be a list from 0 to 10. And now let's make y a list of all the sign values of 0 to 10. So these are the corresponding y values to these x values. Now let's go ahead and plot these points. Now this doesn't look very good. Why didn't this look very good? Because I only did x at every integer, 0, 1, 2, 3, 4, 5, 6, up to 10. I want to have my my points more finely set. I need to have a more finely tuned. I don't know if "tuned" is the right word. I need to have a list that has many more points than just integers from 0 to 10. So now I'll set x is 0 in steps of 0.1 to 10. Now I'll go ahead and hide the output. Now I'll have y is sign of that list. Now let's try plot xy. Again, that looks a whole lot better because I'm not just doing integers now. This from here to here is a list of 10 separate points. From here to here is a list of 10 separate points. So it looks a whole lot better. Now what if we want to use a different color? There are two ways we can do that. I'll start out with the easy way. So I'll say plot x, y. Now I'll just say G. That means it's going to be green. So that's the easy way to do it. Just say G to get green, or R for red, B for blue. I don't know how you get black though, except for this other more complicated way. The more complicated way gives you more options. So now that gave us, we're able to do the RGB values in terms of percentages. So this is 100% R, 0% G, RGB, 100% R, 0% G, and 1% B. 100%, excuse me, B. So we can now use, of course we'd have to do white, that would be kind of stupid, but we could do that. Get black. Get yellow. Any RGB value you want to. This is the more complicated way, but it gives you a whole lot more control. But let's go ahead and go back up to green, G. We could also change the width of the plot. Let's go ahead and go back to G for the color. Using the line width command. See, now this made the line width a whole lot thicker, even thicker still. We can also add a title. And we can add X labels and Y labels. They're kind of cut off, but only because they're so small. If you zoom out a little bit, it looks quite a bit better. See, now I can see X-axis completely and Y-axis completely. We can also add text to any specific point on the graph. So X values, I'm going to put this directly on the graph. So X value is 4. The Y value is sine of 4, so that means it's going to lie somewhere along this curve, particularly about right here. And I could put text. Now I'll put text right there. Oops, didn't mean to do that. Did that wrong. Okay. If we want to start a new figure without erasing all of this, we type in figure. This is figure 1, this is figure 2. Figure 1 set to be always on top. Now let's do figure 2 always on top. So what if we want to plot more than one function at a time? That's where we use the hold on command. This command doesn't erase previous plots, it just puts new plots on top of old plots. So let's start by creating a different plot. Z is cosine of x. See, y is sine of x, now z is cosine of x. So now let's plot xz line width 2. And now let's do x, y, line width 2. Whoops, I forgot to do the actual command. xz line width 2, now I want to do hold on. This will prevent FreeMat from erasing the previous plot. Now I do xy, now it puts, and this one, FreeMat automatically does a different color. I don't know what MATLAB does, but Octave actually does not automatically specify a different color. It's going to go ahead and keep the same color as before. So that's something to keep in mind. When you're using Octave and you want different colors, you have to specify that manually. Now let's add a legend. Oops. So I use the legend command. The first thing put on the figure is always going to be the first thing on the legend. So now we have cosine corresponds to cosine, and then sine corresponds to sine. I don't know if there's a way to make this smaller or larger. But whenever you're done with this video, you should get the basics so you could be able to go on to other places. In particular, probably MATLAB, MathWorks MATLAB website, and look up new options. Now, saving this image in FreeMat is no problem. You just have to click this disk icon, and it'll bring up a save figure as box. Make sure you select what kind of file you want. I actually don't know what a BW file is. Black and white, maybe. But so in FreeMat, no problem. You just click on that. But in Octave, it's a little bit different. I want to go ahead and show you. So I have an Octave terminal here and an Octave figure right here. So I went ahead and did this manually. Let's say I want to save this figure. Go ahead and make this always on top. So you can't just right-click, save as, or anything like that. You actually have to do this through a command, so that's good to keep in mind. It took me a while to figure out what this command was, because the Octave manual, unfortunately, is not very clear on this, but I figured it out eventually. So if I do the print command, and then the number of the figure, which in this case is 4, and then I have the file name. In this case, I'm going to do a PNG file, and then the file format, DPNG. And it's going to save to whatever my working directory is, which in this case is my home directory. Now that's for PNG. That'd be great if you're going to put it online, but if you want to put it in a LaTeX document, you don't want to use PNG. You'd be better off using EPS. So plot.eps, now that gave us a vector drawing instead of a raster drawing. So I know that probably most of you will end up using FreeMat or maybe even MATLAB because you'll probably be using Windows, but this is good to know so that you can know how to do that if you choose to use Octave. I prefer Octave, but whatever floats your boat really works out just fine. Now, what kind of plot you're going to be using, let's go ahead and create a new figure. Make this one always on top too. What kind of plot you're actually going to want to create is going to depend on what class you're in. But for a lot of classes, you're actually going to be getting discrete value points, like from repeated trials from a physics experiment. So you actually won't be plotting functions, you'll just be plotting points. That means that this method for plotting, even though it might seem counterintuitive if you're used to maxima, but this is actually really nice for the hard sciences. Don't get me wrong, you probably will be plotting functions as well, so that's why I went over that. But the idea of plotting lists of points is actually very convenient for a lot of practical applications. So let's say we've collected these points from whatever source we have. And these are the points that we have. So I have in some A values, I'm going to move this out of the way for now. This is our list of our A values, and this is our list of C values, which mostly looks like zeros until you see this up here. This is actually just a lot of pretty big numbers for the most part, actually. So let's try to plot this. Plot A against C. Well, that is supremely unhelpful. That's just really close to zero, and then all of a sudden shoots up. So that doesn't really help us with much. So instead of using that kind of plot, the regular kind of plot, sometimes we want to have the y-axis on a logarithmic scale. And for that we use, in my head I always read this as semi-loggy, but it's just, it's semi-log because it's only the y-axis, not the x-axis. So that is a whole lot more helpful. This plot is a whole lot better than what we had before. There's some what's the word, roughness right over here, but for the most part it's a pretty smooth graph. This one makes a whole lot more sense than the one we had before. So that semi-loggy makes this information now useful. Alright, that concludes this video and probably the video series, unless at some point in the distant future I decide to make some more. I hope this was helpful, and good luck.